We're going to do this afternoon.
Okay, so I got another problem for you. Ready?
Okay.
Okay. I'm going to actually just email it to you again. It's kind of a long one.
Okay. With calculus, unless they're just like take the derivative of this function or take the limit of this, it usually works better if you mail it to me, email it.
Yeah.
If it's a short one, then it's actually not completely, I mean, it helps you to verbalize it sometimes.
Yeah. All right. Send it to you.
Yeah, I got my notification. That's when my phone just went off.
All right. So I'm looking at number 31 on the right side.
Okay.
No idea where to start.
Yeah, this kind of, this is recognizing, does this look familiar?
31?
Does that look familiar to you?
No, it doesn't.
What if I said that that was f of x plus h minus f of x all divided by h, and I'm going to take the limit of that thing as h goes to 0.
That's what that is? Okay.
That's what that is. Now it's all we got to do is figure out what f of x is. And it's furthermore evaluating it at pi over 6.
Okay.
Which is 30 degrees. So the function is sine x. In other words, well, they give you a slightly different way to do it here. Let's do it the way they hint at doing it. Yeah, this is probably a better way. I think this is going to come up with our answer a little bit better. If we use this tip right here, then what they have written becomes that, right?
Yeah.
It becomes sine of pi over 6 cosine of h plus cosine of pi over 6 sine of h.
Wait, what's that first thing you wrote in the first part of that? Sine pi over 6.
Yeah, it's the sine of, in other words, it's all I'm doing is this right here. In other words, theta is pi over 6. When you take the sine of two angles that are added together, that's the sum and difference formula. This is what you get. That is the sum, the formula for the sum of the sine of two angles. With me? Okay.
Yeah.
So, and I'm going to write it like that, and remember that is just that. I got to subtract from that f of x, which clearly is the sine of pi over 6. And then I'm going to divide the whole thing by h and figure out what this whole thing is equal to as h goes to 0. Well, what's the sine of pi over 6?
30 degrees. Wait, no, hold on.
That's true. Pi over 6 is 30 degrees, but what's the sine of 30 degrees? 1/2.
Okay, yeah, 1/2.
Okay, so it is 1/2 times the cosine of h, Well, as h goes to 0, what's cosine of 0?
Cosine of 0 would be 0.
1.
Oh, yeah. Whoops.
If you look at your cosine curve, it goes like that. Okay, it begins out at 1. Sine curve begins out at 0. So the sine of 0 is 0, but the cosine of 0 is 1.
Right.
This right there is this part plus cosine. What's cosine of pi over 6? 30 degrees. That's square root of 3 over 2. What's the sine of 0?
0.
Okay. And now I'm subtracting from that the sine of pi over 6, which is 1/2.
Yeah.
Now, if I do my math, I end up with 0 over 0, which doesn't help us. And why did they give us this hint if it was going to lead us down to that road?
Yeah, good question.
The better tactic I like is the following. I'm going to leave that limit definition up there. We did one of those last time, didn't we, or not?
Yeah, I think so.
Yeah, that's the hardest part of calculus that they start you out with. I think I went through that explanation.
Yeah.
So let's make a guess here. That our function is sine of x. And what we know, if I want to, in other words, the very first thing you have to do to solve this limit definition is figure out what f of x is and f of x plus h. Well, if f of x is sine of x, then f of x plus h is sine of x plus h. Now, if that was true, I'm thinking for a moment. They actually give you a second definition for the first derivative, do they not? Did you not also get this one? F of x minus f of a all over x minus a as x approaches a. That is a more limited version of that. The top one gives you the derivative function as a function of x. In other words, I know the derivative of sine of x is cosine of x. But if I said, what is the derivative evaluated at pi over 6, then we know it's going to be the cosine evaluated at pi over 6. But I can also use this other definition that they have given us. And this definition I never use. It has one purpose to me and one purpose only, and that is when you go to define a corner or a cusp. You know what I'm referring to?
On a graph? No,
Yeah.
I don't.
Yeah, in other words, if I have a smooth function, it's differentiable everywhere. But if I have a corner or a cusp, it is not differentiable at that point.
Yeah.
And it can be anything from absolute value function like that to a situation like the left-hand chart. In other words, anytime you have a sharp edge, it is not differentiable at that. You might think that the slope of the tangent line is like that, or the slope of that tangent line is like that, but it's not. There is no slope of the tangent line. And the way you prove something is a corner or a cusp is with this second definition. If you use this definition to try to analyze that corner, you will see that the slopes are different going in than they are coming out.
All right. So
Kind
can I?
of the equivalent.
I'm gonna
Go ahead.
I'm gonna go ahead and call this problem good. Can I, while I have you, I just know we have limited time. Can we go over another one on this page?
Sure.
Number 21.
Sure. Yeah,
Okay.
I was reluctant to get into this explanation because it's so long.
Yeah.
But the answer is going to be, we're looking at the derivative of sine here. And we know that's cosine, and clearly it's pi over 6 that it's being evaluated at. So it's the cosine of pi over 6, which is square root of 3 over 2. So that's the answer.
Yeah.
Okay.
Sounds good. Yep. So now
what other problem?
Number 21
Okay.
is pretty representative of that whole section, like 15 through 30.
Yeah.
21's just, I think.
Yeah.
So like, would it just be undefined? Because if you plug in 4, that 0 in the.
No, I'm going to go through these techniques with you. Even though we have limited time. Is it okay? Can you go 10 minutes over or not?
Oh, yeah, I definitely can, yeah.
Yeah, well, you started 10 minutes late, so I'll go 10 minutes over.
All right, awesome.
I can't go beyond that, but I can go 10 minutes over. There's basically limit problems where when you do direct substitution, you come up with a number. Those are easy, right?
Yeah.
No problem at all. If I come up with a number divided by x and I'm running the limit as x goes to 0, what is that?
Undefined.
If I have x divided by a number and I'm taking the limit of that as x goes to 0, what is that?
That would be 0.
So both of these are clear, and any number is clear. So there is only one problem, kind of limit problem, and that is when you do a direct substitution, you get 0 over 0. When you get 0 over 0, that's called indeterminate. And you can't determine what the answer is. It's not undefined. 0 over 0 is not undefined. And I'll show you that it's going to end up being a number. But if you plug in 4 for x, you get the square root of 1 minus 1, that's 0, over 0. So direct substitution gives you the classic 0 over 0. Now, how do you handle those? Well, there's 3 basic tech solutions types. One is factoring. This one is not that. 19 is. Can we do 19 first?
Yeah.
That's the more common technique, so I don't want to overlook it. Notice also that when I plug in minus 2, I get 0 over 0.
Yeah.
But if I do a little factoring, which is the main technique, that's why I didn't want to miss this, it factors into difference of squares. And now you can cancel that with that, and you have 1 over t minus 2. And now when you resubstitute, you get minus 1/4. The 0 over 0 turned into a number.
Yeah.
Merely by factoring and canceling. So that's the number one technique you want to remember. And That's the most common one. I could apply that exact technique to number 20. I'm going to make the top t minus 3 times t plus 3. One of them is going to cancel with the bottom. That one, my answer is t plus 3, and as t goes to 3, that goes to 6. What started out as 0 over 0 goes to 6. Okay? So factoring is the most common way to solve these limit problems.
Okay, yeah.
When you see a radical sign, like 21, there's another technique. And you should think of it whenever you see a radical sign. What you want to do is multiply the top and the bottom by the conjugate of whichever either the numerator or denominator has the radical sign in it. So I'm going to multiply by the conjugate, which is square root of x minus 3 plus 1. And as long as I multiply the numerator by that, I got to multiply the denominator by that also.
Yep.
Because I can only multiply by 1. That is my number 1 right there. Now, what happens in the top, I don't know if you recognize it or not, but if you've had a lot of experience with difference of perfect squares factored, that's what we're looking at.
Okay.
So we got to FOIL these back together again, but it's easier than it looks. In other words, when I have a minus b times a plus b, which is what we're looking at, I know that that's equal to a squared minus b squared. That's difference of perfect squares, how it factors. So when you see it in factored form, it's easy to put back together again. That numerator, what's that?
Right, no, you're good.
Okay, so the numerator just becomes square root of that times square root of that is that. Minus 1. That's what the numerator becomes. The denominator becomes, and you don't ever want to multiply these together, even if you could, you can't here, but so I'll just write it out. You with me?
Yes.
Now the top is x minus 4. Now plug in. Now plug in 4 for x. What do you get? Oh, excuse me. That x minus 4 cancels with that x minus 4. And there's almost always a step where that happens. Whether you're factoring or whether you're multiplying by the conjugate, you're going to find a point in the algebra where the numerator crosses off with the denominator. And what I'm left with is 1 over that number. And now when I put in 4, I get 1 plus 1. So the answer is 1/2. Okay? Those are the two primary techniques you're going to use to solve limit problems, other than substitution. Substitution is an obvious one, but it's easy. You use factoring on problems like that. You do multiply by the conjugate when you see a radical sign. I'm going to multiply by the conjugate on 22. Let's look at 23, because this is kind of the third technique. 25, incidentally, I would factor the numerator. That is the sum of perfect cubes.
Yep.
So it factors into x plus 5 times something else. The x plus 5 is going to cancel with that x plus 5.
Yep.
Okay, so let's look at 23. What you have to do with 23 is combine these two fractions. We're going to work with the numerator only for a minute. That's the numerator in 23. And I guarantee you, if I substitute 0 for x, we'll have 0 over 0.
Yeah.
They stop giving you easy ones once they give you a couple. In other words, the moment you get 0 over 0, that's all you ever see again. Seriously.
Yeah.
Okay? Well, how do I subtract these two fractions?
I don't know.
Got to find a common denominator. That's x plus 1. So this becomes x plus 1 divided by x plus 1. With me?
Oh, well, actually, hold on. How do we get from the original problem in 23 to the 1 over x plus 1 minus 1?
That's what that is. That's 1 divided by the quantity x plus 1. That's that.
Yeah. Sorry.
Minus the number 1. And that's all in the numerator. The denominator is still x. We'll get to it, but not yet. Okay?
Yep.
Okay. Now that we've got a common denominator, we can operate on the numerator. Well, what's the numerator become?
The numerator becomes 1 minus x minus 1 over x plus 1.
Okay, so 1 minus x minus 1, the 1's cancel, and I got minus x over that common denominator, all over x. And now I'm trying to figure out the limit of that as x goes to 0. And what's important here, I haven't drawn it correctly. You want to distinguish between the big fraction bar and the little fraction bar. That's the big fraction bar. With me?
Yeah.
Okay. I do this, I'm dividing a fraction by a whole thing, but the way we divide by fractions is we flip the bottom and multiply, correct?
Yeah.
I'm going to put a 1 under that bottom. Now I'm going to flip it and multiply. So it's the same as multiplying by 1 over x. Now notice what happens again with this third technique. The x's cancel, and I'm left with minus 1 over x plus 1. And now substitute 0 in there, and you get minus 1. So 0 over 0 can turn into most anything. It can turn into infinity or undefined. It can turn into 0. It can turn into a number. You never know until you do these additional processes. But these three were perfect. You're not going to find any outside of trig functions that are more representative of what you need to be able to do to solve limit problems. You need to do these three things. You need to be able to factor, you need to be able to multiply by the conjugate, and you need to be able to add and, well, subtract fractions, because you're always subtracting. No, you're not. No, sometimes you could be adding. Yeah, on a limit problem, this is not f of x plus h minus f of x. This is just a straight limit problem. So you could be adding, but in this case, you're subtracting. Okay? But you need to be able to do that. You need to be able to combine those two fractions by finding a common denominator, operating on the numerator, and so forth and so on. And then you're always going to find that that x in the denominator, the primary denominator, cancels out with an x in the numerator. Always happens. Every single time. It's just like every term that doesn't have an h in it, when you're doing that limit quotient definition, every term that doesn't have an h in it cancels out. And the only thing you end up left with in the numerator are h's.
Yeah.
Terms that have h in them, which then can cancel out with the h that's in the denominator.
Yeah. Okay. Sounds good.
So let me see just if there's any others here that are a little different than that. That is 0 over 0, correct?
Yes.
Okay, so the way we need to solve this is to multiply by the conjugate also. We want to multiply this by 1 plus cosine of x, both top and bottom. And notice why. Remember when you used to do your trig? You always multiply by the conjugate because the top turns into 1 minus cosine squared, which turns into sine squared. And that was
Yeah.
why it was very useful to multiply by the conjugate. So this little thing ends up being sine squared in the numerator, and in the denominator we got sine x times this conjugate. And once again, don't ever distribute these. You won't need to, because now this sine cancels with that squared. And I end up with sine of x over 1 plus cosine of x. Now resubstitute 0, and you get 0 over 2. So this 0 over 0 goes to 0 for 27.
Okay. So the answer is 0 in the end?
Yes.
Okay. Where did we start? Like, how did we get to 1 plus cosine x over 1 plus cosine x?
Well, when I look at this, the first thing I do is substitute 0, so I get 0 over 0. And just in my experience with trig functions, you know, back when you were trying to prove trig identities and stuff like that, you would frequently, whenever you saw a 1 minus cosine or a 1 minus sine or things like that, you would multiply by the conjugate. Because when you do multiply by the conjugate, it turns into this. In other words, again, that is the difference of perfect squares factored.
Yeah.
So you want to get used to seeing the reason you multiply by the conjugate is because it'll always turn into a squared minus b squared, which in this case is 1 minus cosine squared, which then turns into sine squared, based on that Pythagorean trig identity.
Okay. So then sine squared over sine x is one of those signs we cancel with the denominator, right?
Exactly. And that's always where you're headed. If you don't have a step in this limit process where you're not canceling a numerator and a denominator, you probably made a mistake. We've done 4 types of problems. That kind, that kind, that kind, and now a trig kind. And every single one of them, a critical step in the process was canceling this denominator that you have or a numerator out with a similar factor on the other side of the fraction bar.
All right.
So yeah, you might not think of this in 100 years if somebody didn't show you that, because that's not an obvious solution at all. In other words, when you see this problem, you don't immediately think, I'm going to multiply by 1 plus cosine x over 1 plus cosine x. The only reason is that that's a very common trig maneuver when you're trying to verify trig equations. And it happens to be very useful when you're trying to solve limit problems involving trig equations also.
Yeah. Can I ask you one more question?
Sure.
On number 33, where you just plug in the 2 values for f of x and g of x, and then you have to find the limit as x approaches c. Like, how do you know, because c is not a defined variable, so like, how do you
evaluate the limit given that f of x is equal to minus 3/4 as x approaches c, and the limit of g of x is equal to 2/3 as x approaches c. And the rules of limits are the product of limits is the product of each limit. So the answer to this is minus 3/4 times 2/3. In other words, the limit of f of x is minus 3/4. The limit of g of x is 2/3. They're asking you what is the limit of f of x times g of x as x approaches c. That could also is the same as saying this. That's the limit of f of x as x approaches c times the limit of g of x as x approaches c. In other words, that is the equivalent of 33.
So I guess I'm just asking, like, how would I write my answer?
Well, they tell you what this is, right? That's minus 3/4. So I'm going to replace this whole limit with minus 3/4, and they tell you what this is. This whole limit is 2/3. So I'm going to multiply minus 3/4 times 2/3. So I get minus 6/12, which is minus 1/2.
Negative half, okay. All right. I think I got that then.
Okay.
All right.
Cade, nice working with you today, and I'll let you schedule whenever you want another session.
All right. Thank you. I appreciate it, David.
You're welcome. Bye-bye.
Bye. Have a good day.
You too.